Hello everyone, my name is Bella and I'm a PhD student at Arizona State University, and I'm here today with my lab mate Jacob to tell you guys a project that we put together where we built a radar system using a software-defined radio and GNU radio that's capable of sensing heart and respiratory rate. So Jacob and I, like I said, we're from Arizona State and we're part of WISCA labs under Dr. Daniel Bliss. So these are the topics I'm going to go over today. But before I get into too much technical detail of the actual project, I'm going to give you guys a little bit of a background on the physiology of your lungs and your heart, which is a little bit outside the realm of what's normally talked about at this conference, but thought it might be good to build up a little bit of a background. So when we breathe, we're bringing oxygen-rich air from the environment into our body and expelling the carbon dioxide out of our body, and the way that we do this is by contracting our diaphragm in a way that expands, that pulls your lungs down and causes your chest wall to expand. This creates a negative pressure inside of your lungs. Because of that negative pressure, the oxygen from the environment is able to flow into your body. And then when you want to expel the carbon dioxide out of your body, you allow your diaphragm to relax, and this causes the carbon dioxide to expel back into the environment. And a typical breathing rate for a healthy adult is 12 to 20 beats per minute, but this can vary significantly depending on if you're exercising or relaxing, and then also person to person. But significantly higher or lower rates can signify different disease states, and for this reason, it's an interesting metric to keep track of. So now switching over to the heart. So your heart is a muscle, and it contracts for the purpose of circulating oxygen-rich blood to your tissues and then bringing the oxygen-poor blood back to your lungs. And the way that it acts in this pump is by the muscles actually physically constricting. And so this is a movement. So when you hear about your heartbeat, what is being counted here is that contraction of your heart muscle. And a typical resting heart rate is about 60 to 100 beats per minute in a healthy adult. But this also varies significantly depending on if you're exercising or relaxing, and then also person to person and over time. But significant changes in your heart rate over time or resting heart rates a lot higher or lower than this range can also indicate different diseases. So for that reason, this is also a vital signs that's often kept track of. So traditionally, your respiratory rate is monitored just with like a physical count. So if someone's just gonna watch a patient or a subject and stand and look at their chest and watch how many times the chest moves forward and backwards. And this is a intermittent measurement that's completely subject to human error also. And because the person has to actually like take part in it at all times, it's only tracked, it's very rarely tracked, and often in a clinical environment, they don't keep track of it at all. But it is a meaningful vital sign, so there's motivation for a better way to keep track of this. And then in parallel to that, the heart rate is typically monitored using an electrocardiogram or an ECG, which this is a measurement, or this is a measurement that measures the electrical conductivity of your heart. So when those muscles in your heart are contracting, there's electrical impulses that are firing in a way that you can track what's going on. And the way that this is tracked is by attaching electrodes directly onto a person's skin. But there are drawbacks to this in that it's kind of uncomfortable, and also like if you're in a clinical environment, it's hard to interact with a patient that's wearing these, and you kind of need to be in a hospital or something in order to have this measurement taken. So an alternative way that the heart rate's often measured is with the PPG, which this is an optical measurement. So you're actually shooting some kind of optical wavelength towards the skin, and it's measuring the absorbance of that light that's sent at your skin. And the absorbance differs depending on how much blood volume is in your extremities. So when your heart beats, blood rushes into your extremities. So there's more blood in your like fingers and toes right after it beats, and that's what that measurement's measuring. So if you've ever worn a smartwatch or a pulse oximeter, that sensor in the middle there, that's the measurement that this is taking. But both of these are contact-based, or all of these are contact-based or intermittent. So for kind of obvious reasons, there's definite motivation to be able to monitor heart and respiratory rate without contact in a continuous fashion. So for that reason, for many years now, people have started looking into using radar to monitor your vital signs. So the idea behind this is that you can transmit a radio signal towards a subject, and their chest wall moves in a way that modulates the transmitted signal, and that modulated signal at the receiver contains the information of your heart and your respiratory rate. So I'll go into that a little bit more on the next slide. So if you look at the guy here on the screen, you'll see that there's that red wave coming through the air, and then there's an orange wave coming through the air. So picture that the red wave going first, and at that point in time, the subject's chest is recoiled, and then at a later point in time, that orange wave is what's being reflected off the chest, and the chest is expanded further. And so because that distance has changed, the location that the two waves hit on the receiver, or that triangle in the middle of the screen there, has changed. So according to Doppler theory, if you reflect a tone at an oscillating target, in our case the chest, it's going to return in time with time-varying phase that's proportional to the displacement of the object. So if you imagine now that that receiver that's in the middle of the screen, you flipped and now you're looking at the front phase, that tip of the phaser there, so the edge of the arrow, is going to oscillate with time depending on how far away the chest is. So for this reason, you're able to track the way that the chest wall is moving, and that's going to contain the information of your heart and respiratory rate. So over the last several years, a lot of research has gone into this area using many different approaches. So what I explained on the previous slide was unmodulated continuous wave radar. But there's also a lot of other types of radar that have been used for this, including frequency modulated and ultra-wideband pulsed radars. And then there's also a lot of interesting research right now that's going on using phased arrays and MIMO configurations in order to monitor multiple subjects at one time. And then in combination with this, the post-processing techniques that you use to extract the heart and respiratory rate from the received signal vary a lot. And most of the research to date has been done using specific hard-coded radar sensors, like these pictures that you see on the your right side of the screen. And in the WSCA labs at Arizona State, we've been doing a lot of research in this area, and that's how I kind of got involved with this lab, is because my research interest is in biomedical signal processing. And in addition to heartbeat, we've also used radar to monitor other signals of the heart, including your RR interval and then the acoustic signatures of the heart, which these are correlated with even smaller movements, so that's been very cool. And then we've also been looking into multiple subject monitoring using MIMO configurations, so separating and localizing to monitor multiple subjects at one time. And then more stretched, challenging situations such as exercise monitoring. And a project that we've recently worked on is through-wall monitoring, so being able to transport your radar sensor around the edge of a building and be able to tell if there's people inside of it. So that's got defense application and search and rescue type applications also. So those are all really cool, and this is really exciting research, and I absolutely love it. But there are some difficulties that we've come up to, which kind of brings us to our project here today. So most of the research that has been done in this area, as I've kind of hinted at before, has been done on custom hardware, hard-coded radar sensors that are built to transmit one type of waveform in a limited frequency range, or with very tight control over things like pulse repetition intervals and bandwidth and things like that. So a lot of times we have found ourselves in a situation where, okay, we're doing this, and now we wish that we had control over this certain parameter of this radar that we have, but we can't reconfigure it easily on the radar sensor that we have, so then we go back to the drawing board and find a new sensor to work with. But Jacob over here is kind of a SDR expert, and he's also a member of our lab, and over the past year we've kind of started thinking in the back of our heads is like, we should start using the software-defined radios as radars for this purpose, so they don't have to constantly be going and looking for new radar sensors, because software-defined radios allow you to very easily reconfigure or just give you all the control that you don't have with those other sensors. An additional benefit that we see to this project is that software-defined radios are pretty accessible, especially like at universities and such. So a lot of people have access to a software-defined radio, and then in combination with GNU radio, it's pretty easy to set this up. And this is like very, like obviously I think this, but super exciting research, and it's very fun application. And we wanted to like do our project in a way that got other people excited about it and was very easy to follow, so that other people in other places can start looking into this also. Because the more people are working on an issue, the more quickly it can innovate, and the quicker that we can actually see it through to something that's used in everyday lives. Because the signal processing approaches still need to be kind of robustified before they're actually implemented in hospitals and such. So some future extensions that we hope to do. What we set up for you today is just a simple, like the simplest test case of vital sign monitoring using just a continuous wave, unmodulated tone, bistatic radar. But in the future, we want to start looking at different waveforms and shorter wavelengths. So we're getting some new radios in the lab that will allow us to go into the millimeter wave range and more easily configure MIMO type setups. And then also explore new and improved signal processing approaches, which GNU radio will help us implement those very quickly. And then something else that I want to kind of like emphasize here is that this was like, I mean, no one wants to say this about when you do a research project, but this was relatively easy to set up. Like, this is simple, especially with like GNU radio. We put this together and like innovated on it in like it took a while, but like the actual like demo that we're doing was like a few hours of work just to get this like set up. So it's very accessible, it's really cool, and we want to get other people excited about it also. So now I've talked a lot about background. I'll actually explain the experiment that we did for you. So we used, what we have here today is just an EDIS-USRP B210 and 2 horn antennas, and I'm going to have Jacob sit here, and he's going to breathe, and we'll display it for you, and you'll be able to see his respiratory rate very, very obviously, and then the heart rate will be a little bit more difficult. But the general signal processing approach that we take is we are capturing the complex baseband signal on the receiver, and then we track the phase of that versus time. So if you look at the blue line here on the left graph, that's just the phase of the received complex baseband signal versus time. So the peaks and valleys of that correspond with the chest expanding and relaxing. And then, I'm sorry, it's crackling a little bit. I'm not really sure why. The kind of smaller oscillation, you can see like little twitches on top of the like the higher frequency wave riding on the chest movement correspond with the heart rate. So that's a little bit harder to extract, but you're also able to do it. So the first step in our signal processing approach is to remove the DC offset that happens as a result of like the phase wraps every 2 pi, and there's some like slight motion of the subject that can cause it to kind of shift over time. So first thing we do is we did a polynomial fit to remove the DC offset, and then you can look at that versus time. And then we want to transfer it into the frequency domain, so we do that with a FFT. And in this data that you're seeing on this screen, the subject, if you were to count the peaks and valleys, took 16 breaths in a minute. So when you do move it over to the frequency domain, you see a very sharp peak at 16 breaths per minute, and this corresponds with the respiratory rate. But then a characteristic of the FFT is that you see harmonics at integer multiples of that value. So you're seeing a few harmonics of the respiratory rate pop up in the area that we're looking at for heart rate also. So this is kind of a slight difficulty with our current setup, is that sometimes the respiratory rate harmonics are of similar amplitude as our heart rate peak. But you can still see, so like in this data right here, the subject had a heart rate of 68 beats per minute. And you can see a definite noticeable peak at 68 beats per minute. So it's interesting, but there's still room for future improvements, and we're hoping to implement a lot of the research that we've already done in our lab on using software-defined radios, and then continue to improve upon it quicker in that way. So without further ado, we'll set up our demo for you here. Okay, so we're just transmitting a complex tone, and Jacob's gonna breathe, and the top plot here will just be the phase versus time. It takes a few seconds of lag before it starts to pop up, but you'll see it in just a second. And then the middle plot is the DC trend removed, and then the bottom plot is the FFT of the signal.
So it's just a simple flow graph. You put a cosine in and you get a cosine back bounced off, and then you just track the phase. And so it bounces every time I move way too much. So there it was for a second there. You saw my respiratory rate. I'm breathing at about 16 to 20 breaths per minute. But then if I actually sit still for about 30 seconds, you'll see my heart rate start to come out, and it's way high right now. So you probably see it come in around 70, 75 beats per minute here. So I'm going to attempt to sit still, which is hard for me because I'm nervous up here. But we'll see what happens.
Yeah, it'll start to come through. So now it's starting to flatten out, and you can see the peaks there correspond with his breaths. Let me know when you start holding your breath. So if he holds his breath, you'll be able to see his heart rate a lot clearer because it's not varied by the respiratory rate. So there you go. Now you're seeing those peaks right there are heart rate, heartbeats on the top plot. So, yeah. So all the little peaks there correspond with heartbeats.
You can see the little heartbeat right down the middle there. In the middle plot, you can see just the heartbeat writing once it's been filtered out and processed a little bit. And then because my FFT on the bottom is poorly scaled, you can see a peak at the bottom. And if we flip over the output, we'll see it's estimating somewhere between 6 and 16, and then my heart rate there at 70 during that 70 period. Otherwise, it's just making estimates of my respiratory rate. So there's it just chugging along on stage.
Yeah, so we'll keep that fired up there for a minute, but try not to knock this over. Does anybody have any questions?
Hi, I have two questions.
Yeah.
The first one is, why do you choose 4 gigahertz?
Why did I choose 4 gigahertz? So, main reason is that that's what worked best with the antennas, and is about as high as we could comfortably go with the software-defined radio that we used. So the higher frequency that you go into, the smaller, here, let me go back to the equation. Yeah, so the smaller distances you can measure, but with larger changes in phase. So as your wavelengths get shorter here in this equation, the very small changes in distance will cause larger changes in phase, which means that very small movement of the heart is going to make a bigger oscillation there. So that's something we want to look forward to more in the future is going like more into the millimeter wave range, which we're going to be able to do once we get. What? Yeah.
My second question is, how much power do you transmit and what is the level to be harmful?
Power transmit.
Power level.
Not a lot. Less than a milliwatt.
Do we have more questions? We have some time. Oh, there we go.
Any idea, or have you guys had any thoughts about how you might deal with motion correction, like for a subject who's moving besides breathing rate?
Could you repeat that? I'm sorry.
I was wondering if you have any thoughts on how you would deal with subject movement, like somebody who is moving around besides just their chest.
Yeah, so that's definitely a more difficult situation is when there's a lot of movement going around. So what this is capturing is oscillations. So a lot of movement is not an oscillation so much as like a jerk or a jitter. So for that reason, a lot of times you can look at the data and see like some kind of big jump or something and say like if this happens, that's probably not a heart rate or a respiratory rate. Like that's not what it would normally look like. So we have some people in our lab looking into some like machine learning type stuff to be able to kind of catch when that type of thing happens and then throw it out. But it still needs to be improved upon also.
Another fun method for that is using a range Doppler radar and then picking out a bin that's relatively stable is actually target tracking, but you end up needing an inordinate amount of bandwidth for that, hence the move to millimeter wave for future experiments and pushing it to the limit there.
I know. I might have missed this, but you're not wearing like a metal patch or anything to enhance the reflection.
I have a poly shirt on or whatever.
Okay. I wonder if that. I had a similar question to him, but I think you guys answered it pretty well on like smart ways to like reject like clearly wrong heart rates and or respiratory rates. I wonder if you had something like like a retroreflector. Like an RFID type thing, that if the enhanced reflection might not allow you to, I don't know. I just wonder if that would help with rejecting some of those bigger motions. But I'm not an expert in this.
Yeah. So we've actually thought about that.
Can you please move closer to the mic?
Oh, we've actually thought about that a little bit in putting a little gold or similar implant near a heart rate or a pacemaker even. Style thing to be able to actually improve your motion cancellation or tracking ability for a subject like a human. So we've done some early modeling on how those waves go through, penetrate the chest and are reflected off of it. What kind of other effects aren't we anticipating from the human body and the flesh? As it behaves differently than a lot of other traditional materials that we reflect stuff off and experiment with in the radar community. So yeah, we've looked into stuff like that and it looks promising for some approaches, but it's also undesirable for other reasons. So you have to balance your approaches there.
Yeah, there could definitely be some benefits, but one of the main completely contactless nature, which that kind of retracts that element of it.
Hey, I have one more question regarding the frequencies that you
Yeah.
use. So I know in medical environments, there's a lot of medical equipment ongoing, and some of the things you need to make sure before you get FDA approval to use on a patient is that you're not going to interfere with anything that's, life critical. Have you gone through an analysis of what spectrums, what available bandwidths you could use for doing? I know right now 4 gigahertz works with what you have for demonstration, but for future applications.
We haven't gone too far into depth with that, but like we said today, we're transmitting very close to the range that like Wi-Fi is in, so like that's already allowed, and like you can use that. But yeah, you can.
But it's also an issue to be in those Wi-Fi bands. You get jammed quickly and you struggle. I know that the medical field is pursuing lots of 5G in branch for kind of the Internet of Things connectivity and ultra reliable connectivity. And those bands are actually, until you get to FR2, they're not particularly reasonable for this, because at the end of the day, you really want to be up at millimeter wave frequencies to get the resolution you want and realize the performance for these kind of systems. So as far as I know, the medical field isn't strongly interested in FR2 yet in deployments, but it's a good thing to anticipate. So thank you. Appreciate bringing it to our attention.
All right. You have another question? Okay, good.
Particularly with contactless monitoring, I don't know if you've looked into it yet, but neonates, one of the things that they typically use is adhesives to adhere to the skin, and it's very fragile. For something like this, neonatal unit would be prime focus of.
That's actually how I got involved with this. Is my undergraduate research was in this application for neonatal ICU environments, and our lab in Arizona has started kind of a spin-off company that's looking into that application specifically, because you're absolutely right that ECG electrodes often tear at their skin and make it very hard for the nurses and doctors and their parents to be able to actually hold the babies. So that's like an ideal application for this type of thing.
All right. If there's a short question, we can maybe squeeze it in. Otherwise, I'm going to ask the next presenter to slow. You have a short question? Okay. But Joshua or something, Joshua Mack, I think, is the next presenter. Maybe you can start walking towards the stage.
Have you guys tried benchmarking against traditional ways of measuring those, and how do your results compare?
Yeah, so in our paper, there's actually a little bit of a discussion about that. So in the radar that we set up, this is, like I said, as simple of a system as you can set up. And it can get respiratory rate pretty much completely correct. What we said in our paper, we said that we got it within about plus or minus 5 beats per minute on the heart rate, which is pretty decent, but it's not as high as what the PPG what a conventionally available PPG can do at this point. But we're hoping when we start being able to set this up in the millimeter wave range, which is what we have used for most of our actual hard-coded radar sensors, we'll be able to improve upon those results.
Well, we love demos. I think this might actually be the first sort of biomedical demo we had live on stage at GRCon, so that's the first. And for that alone, but also for your great talk, I'd like to get a big round of applause for our speakers.